Hi everyone. In this video, I want to do a few computations to understand multi-class logistic regression a little bit better and also neural networks, simple neural networks a little bit better. So here are the equations Z1, Z2, Zk. So there are linear equations. And how do we get soft predictions like probabilities is by given an input, we apply this linear transformation, which give us the vector z1, z2, zk, and after that we apply a softmax function to get probabilities. So yeah, kind of one question I have for you is like, what is the boundary of this? If you have the RD, which is our space which X lives, what are the boundaries of these predictions? Like if you make like hard predictions, what are the boundaries of these predictions? So I wanted to kind of use an example to understand that. So suppose that we have these z1, z2, zk. So as we said before, to get a y hat, what we're gonna do is to get a soft prediction, we're gonna do softmax of z1, z2, z3. Now to get hard predictions, what we're gonna do is to do argmax. We're gonna find the maximum between z1, z2, z3, and we're gonna call that the class, right? The class. So argmax of z1, z2, z3 would be our kind of hard prediction. So I want to figure out what does this looks like for this particular example. So you guys gave an intuition of how to think about that. So let's draw a little bit here. So the first thing that we have to notice is that the prediction are given by the maximum between z1, z2, and z3. So unless this maximum changes, these predictions are gonna change. So, and the places where this maximum could change is basically in places where z1 is equal to z2, or z2 is equal to z3, or z3 is equal to z1. So the only places where predictions could change are places in which this happens, this equality happens. So for example, in one part of the space, maybe the class C1 is the best, right? And maybe at some point Z1 gets closer to Z2 until they are the same, and then maybe Z2 is basically the bigger class, and so on. So I want to figure out how this actually, in this example, how this looks like. So the first thing we have to do is to understand like these equations: z1 equals z2, z2 equals z3, and z3 equals z1, and understand that in our space in R2, right? And we're gonna draw those boundaries basically, and then we're gonna figure out in each of these regions what class it belongs to. So let's start with z1 equals z2. So I have here 2x1 plus x2 equal x1 plus x2 plus 1. Okay, so we can cancel, so start here, cancel these two cancels with this, and we get x1 equal 1. Okay, that is coming from here. So now let's do z2 equals z3, that is x1 plus x2 plus 1 equal to x1 plus 2x2. Okay, so this simplifies a little bit, this simplifies with that, and we get x2 equal 1. Okay, and finally let's do z3 equals z1. We have 2x1 plus x2 equal x1 plus 2x2, and so this gives you x1 equals x2. Okay, So let's draw these equations. So first of all, I'm gonna have, this is my my axis. So this is x1, this is x2. Let's say that this is 1 here, and this is 1 here. Okay, and we have x1 equal x2. It's just a line. And then we have x2 equal 1. It's this line here. And then we have x1 equal 1, which is this line here. Okay, so we have like 3 regions. So we have regions, let's call this region 1, region 2, region 3, region 4, region 5, and region 6. So because of the argument we were talking about before, really if we take any point on those regions and we compute z1, z2, z3, we take the maximum. That's just should be, basically you take the maximum class. That should be the class of the whole region, because the only places in which that class can change are these boundaries here. So we're gonna take a point for every one of these regions, figure out what the class is, and we assure them that this is the class of the whole region. So let's look first at region 1. So region 1 is the region here. Right, so I draw that region. So let's take one point. Actually, let me draw a little bit and forget about this. So let me just like this. Okay, so let's take a point in that region. So let me keep my computation here, right? So let's talk about region 1. Let's take a point on that region. So a point on that region could be, for example, x1 equals 0, which is this line here, and x2 equal 2, because this is the line x2 equal 1. Okay, so let's understand what these numbers are. So is z1 in this case is gonna be 2 times 0 plus x2, so it's gonna be 2. z2 is gonna be 0 plus 2 plus 1, which is gonna be 3. z3 is gonna be 0 plus 2 times x2, which is 4. So the prediction is class 3 in this case, because we have z3 which is bigger than z1 and z2. So the prediction here will be class 3, and that would be the prediction for the whole region. Okay, so let's go to region 2. In region 2, we have to find a point in region 2, and so we can also again maybe do x1 equals 0, but then we have to do x2 equal 1/2, because it has to be, because this point here is 0, 0. This point here is 0, 1. So a half is in here. Okay, so now let's compute, so that would be 2 times x1 plus x2. So z1 is going to be 1. So in the other one we have like 1.5, z2 is equal to 1.5. and in the next one we got z3 equal 1, 3 equal 1 because it's 2 times x2. So in this case it looks like we have class 2. Okay, so let's the computations are fine. This is 2 times actually z, actually this is a half because is 2x1 plus x2, so z1 is a half, z2 is 1 plus a half, which 1.5, and z3 is 0 plus 2 times x2, which is 1. So basically this is class 2. Okay, I am gonna let you guys finish this computation. I am going to tell you what I get, so let me know if this is something that is similar to what you get. But I get I get that 3 gives me class 2 as well, so region 3 gives me class 2, region 4 gives me class 1, region 5 gives me class 1 as well, and region 6 gives me class 3. Okay, so then what we got is that we have these regions that the boundaries are kind of linear pieces, right? So, and that's how basically how the space of R2 is divided when you have 3 classes. Okay, so I hope this gives you an intuition how multi-class logistic regression, what's the boundary of that. So next I wanted to do a computation on a small 2-layer neural network. So what is a 2-layer neural network? So first we apply a linear function transformation to the input, then we apply a nonlinear function, then we apply another linear transformation to the input, and then finally another linear transformation at the end. So here for simplicity, what I have done is that I am considering h of a and sigma of a to be 1 if a is bigger than 0 and 0 otherwise. Okay, so it's an approximation, like it's not a sigmoid, it's personally a nonlinear function. And this will make our computation a little bit simpler. In reality, we will consider more like continuous functions that are differential almost everywhere, but it's just to make our computations a little bit simpler. Okay, so let's actually so these are the equations here, so I'm gonna be going back and forth, but the first thing we're gonna do is that we have these 4 points here, and we're going to compute. So we have these 4 points, and we're going to compute the values of this neuron for all of these 4 points. So, and the values on the neuron are these numbers here. So we're gonna do, for example, x1 times 20 plus x2 times 20 minus 30. Okay, actually let me write this down. So to compute z1 we're gonna do 20 times x1 plus 20 times x2 minus 30. Okay, so the first one is going to give you minus 30 because it's 0 plus 0 minus 30. The second one is gonna give me minus 10 because it's 20 minus 30. The third one is gonna give me minus 10 as well. And the last one is gonna give me plus 10. Good. Now let's compute the values for this neuron on these 4 points. Okay, so Z2, Z1, Z2, 1. So the top number corresponds to the layer. The bottom number corresponds to the dimension. Okay, so we are in the layer 1 here. It's layer 1, and this is layer 2. Okay, so and Z1 is a vector which is Z1, 1 and Z2, 1. Okay, which is what we're computing here. So but for the second one we have like minus 20 times x1 minus 20 times x2 plus 10. So in the first case we get 10. In the second case we get minus 10, right? Because we get minus 20 plus 10. In the other case we also get minus 10 because we get minus 20 plus 10. And in the last case we get minus 30, right? So because we get minus 40 plus 10. Okay, so now we have to apply the nonlinear function, the one we have in here. H of A is this one. And basically it's just saying anything that is bigger than 0 is going to be a 1, otherwise you're going to have a 0. So minus 30 gets a 0, 10 gets 1, minus 10 gets a 0, 0, 0, 0, 1, 0. Okay, now we're going to apply our second layer to the input, this input A1 and A2. Okay, so we computed this. After that we apply to that a nonlinear function, and then that's the input to our second layer. Okay, so in the second layer we have Z2, which is just one number, okay, is equal to 20 times A1 1 plus 20 times A2 1. So in the first case, okay, minus 10. Okay, so in the first case we have a 0, 1, so we will get 20 minus 10 is a 10. Okay, so in the second case we get 0 minus 10 is minus 10. Minus 10, remember that I'm applying it to this part here, and then we get a 10. Okay, and finally we get our sigma is also 1 if A is bigger than 0 and 0 otherwise. So we will get a 1, a 0, a 0, and a 1. Okay, so let's actually make a little drawing of this, what this function is doing. So we have our x1 here and x2 here. So in 0, 0 we're getting a label of 1. Okay, then in 0 0 1, we're getting a label of 0. So this is, let me give myself, x2, we're getting a label of 0. Okay, so then basically on 1, 0, we're getting a label of 0, and on 1, 1, we're getting a label of 1. So as you can see here, this is computing kind of a non-linear function, because there is no way of, no line can divide the two ones from the two zeros. Okay, instead of using h and sigma to be this number, you can use h and sigma to be a sigmoid function, and you would get an approximation to this function that we are constructing here. So it's going to be something non-linear that is so in which it's difficult to separate the predictions that are going to get a 0 from the predictions that are going to get a 1. Okay, so this is the example that I wanted to talk about. Thank you, and see you in the next video.